So this lesson is going to focus on acids and bases that can either lose if they're an acid more than one H, or if they're a base, take in more than one base. So far in this course, we've been largely looking at monoprotic species, mono being one, something that just takes in one or loses one. So something like hydrochloric acid is monoprotic. Okay. I'll use the Arrhenius equation. It's simpler to put into a small amount of space. That's an Arrhenius equation to show the monoprotic, the loss of one H. Modified, I would have put in water. We're going to talk about polyprotic species now. Okay. The poly just means many. Okay. Now acids are, if they're polyprotic or a base, diprotic is going to be the most common. There's a few triprotic, they're quite rare, and you're not going to see more than 3 in this course, and you'll rarely see 3 or more happening in nature with solutions. Okay. Now we use the word poly both with acids and bases. Okay. It could be a transfer of an H ion sort of out, which would be an acid, so losing many, or you could have a base, which would be taking in more than one H from water. Now, these transfers happen one at a time. So if something is diprotic, we're going to write 2 equations to understand it. Or triprotic, we'll write 3 different equations showing each transfer. For triprotic acids, okay, so we're losing, for polyprotic acids, we're losing more than one H. The first H that comes off is often, not always, but often 100%. That's the least important statement. The next one is really useful. Even if something is not in your table, the second and third or fourth hydrogen that comes off is always less than 100%, which that is our meaning of weak. So the first polyprotic acid I want to talk about and write the equations for is sulfuric acid. This is in your Alberta Chem 20 data booklets. You could get the formula. You don't have to memorize it, though in Science 10 you should have learned the acid naming rules, whether they start with hydro or whether they don't. Okay. So sulfuric acid is based on sulfate, and you need 2 hydrogens with sulfate. Okay. The ic comes from the 8. Okay. Okay. I'm going to do the modified Arrhenius. That's the best true picture of acids and bases, as long as they're not a strong base with hydroxide. So we've got our sulfuric acid. It's going to react with water. We're going to transfer not both, one of those H's away. I'm always going to be writing one at a time. So we'll send one to water. That'll make hydronium. And what's left over still has one H left. We go from 2 H's down to 1. We still have the S, the O, 4, and the charge would drop 1 from 0 down to -1. Now, sulfuric acid is in your table, and it's labeled, it's at the top, above the gray line. So this acid, this transfer is 100% for the first H. So if we had 1 mole per liter of sulfuric acid, that would turn into 1 mole of hydronium. You could figure out the pH. The second H does come off. We see HSO4 minus in our table. We don't need to check in our table to know that it's weak. We know the second one has to be weak. So HSO4 minus, which is a product of our first ionization. Okay. So the first ionization has to occur, and then this can react with some more water. We transfer away the second H to water. We make more hydronium, very little more, but we do make a bit more, and we take away the second H, and we're left with just sulfate. Okay. And this is weak, less than 100%, and it's going to be a fraction of a percent. Okay. It's so weak, it makes so little hydronium, it wouldn't even affect the sig figs in your first step hydronium, that 100%. There's no more H's left, so sulfuric acid is a diprotic acid. There's only two. So that is nice modified Arrhenius that illustrates the two transfers. I'll do one more polyprotic acid, and then we'll talk about polyprotic basis. Phosphoric acid is a triprotic acid. H3PO4. I'm going to stop putting all those green arrows from the acid to the water. I'll transfer the first of three H's. We're going to get hydronium, and we'll go from 3 down to 2 H's. The PO4 is never going to change. We drop our charge by 1. Often, sometimes the first H comes off 100%. But if you find phosphoric acid in your relative strength acid-base table, it is in the weak section. So this one does not come off 100%. It's less than 100, it's weak, so it requires chemistry 30 to figure out how to calculate the hydronium and the pH. That's not going to be a Chem 20 skill. Now the species with 2 H's can do another loss. We see H2PO3- in our acid table. Now in our table, it is much lower, and it's always lower. Every time you take an H away, you're going to find it lower in the table. It's going to get much weaker. So we had 2 H's, we're going to be down to 1 H on the product side. We were minus as a reactant, we're going to drop another 1, so we're going to be -2. This is going to be much less than 100. I'm just trying to emphasize the fact that it's much weaker. I'll put an arrow in now, going down, that each of these reactions I'm going to write are weaker and weaker. Okay? Even the first one wasn't strong. Maybe we're 1 in 100 at the beginning, we're 1 in 10,000, and then we're 1 in 100 million. One step to go. I'm doing the same type of pattern. I'm going to take the product that has 1 H, and I'm going to transfer the last H away. So I directly copied the black underlined product. In its inner data table, it is the worst acid we have in our table. But it is still an acid. And now we're going to be at the end. Our product has no H's left. PO4, 2- drops to 3-. And we're done. We have no H's left. This is a triprotic acid. Okay. Much, much, much less than 100. I just want you to know, I keep saying it, that they get weaker. So moving on to basis, and we're on the theme of polyprotic species, all your polyprotic bases are going to be weak. Okay? Now, I'm not counting calcium hydroxide that's strong, that just dissociates into two. Okay? You do have to watch out for those group 2 cations with hydroxide. Okay? But polyprotic bases take in 1H. When that's done, they take in a second. Okay? And there's no strong examples. So we're looking in our weak base section above hydroxide in our acid base strength, or the base column of our acid base strength table. So I'm going to do an example of the 2 accepting of H's for the carbonate ion. Now, if we're talking about this on a quiz, we might be talking about sodium carbonate. And then that sodium ion would be a spectator ion, would do nothing. So I'm just going to start with carbonate, which is in your base column of your acid base strength table, 3 up from hydroxide. It's the 3rd best of the weaks, the 3rd best of the less than 100s. So carbonate plus water. I will put my green arrow in. This again is a strategy, a tool. It's not really part of an answer. But bases are going to take one of the H's from water, and we typically write it in the front. Okay, we're only taking one of the 2. So our base is going to go from 0 H's up to 1 H. And I was dropping the charge before with our acids. We're increasing the charge by 1 with our bases. That water's been ripped apart, and there's 1 O and 1 H left. And it's negative, its charge drops. Okay. So that's our first transfer, and this has to be weak. Okay. I'm just going to switch to, I wrote less, I could have written less than 100. I'm going to write weak, which has the same practical meaning. Okay. Less than 100 is a weak species. Okay. This is polyprotic because this negative ion is capable of taking in another H. Okay. It is in our base column. So I'm pointing to carbonate, 3 up from hydroxide. If we keep going up, which is weaker in our base column, we get to HCO3 as a base. So your table is your guide to whether something is going to be di or triprotic, or the question might tell you phosphate is a triprotic base. Show me 3 equations, where you don't have to look it up. With the basis, it can be quite handy to put the arrow in as a cue. Students are pretty successful at taking the H away for acids. They sometimes get confused with the basis what to do. So that's our guide. So we're adding a second H. So we go to H2, CO3. The second exception, or adding to the base, is going to be weak, and it's going to be even weaker. We have that same pattern where as we either accept or lose H's, they keep getting weaker. And that's going to be my one example of a diprotic base. Hopefully you've seen enough examples now to pick up the patterns. So just make sure your mind is set whether you're gaining or losing H's. You realize the second ones are weak. If it's a base, they're all weak and getting weaker. Start. We can tell a strong acid from a weak acid if we can set up an experiment correctly. Okay. Now, we often talk about manipulated and responding variables a lot, but good experiments hinge on controlled variables. Chemists have it a little easier with controlled variables. In biology, it's often incredibly difficult to control variables because the variables are often living organisms or cells. So I want you to think that I'm going to recap how would the pH of a hydrochloric acid solution to a hydrofluoric acid solution. Okay? Now, hydrochloric acid is strong, HF is weak. Now, we need to add a bit more pieces to this than just having the two acids. So I want you to think, if we want to tell, what would we expect with the pH and how could we ultimately tell a strong acid from a weak in terms of variables? What would we want to manipulate? What would respond? And then really, I'm going to make you think of the controls. What would you need to control? Okay. That's where we have just a white space. Okay. Now, the manipulated is inherent in the question. The manipulated, we're varying the strong acid and the weak acid. So the type of acid is our manipulated variable. Okay. We want our responding variable to be pH. But in order to do that, I'm going to leave you to think, what controls would we want to have when we do this measurement so that the pH does connect to the strength and not just be random? Okay. So I'm going to summarize those controlled variables with a bit of short forms. Okay. So we started off with the concentration. That absolutely must be controlled. Okay. Number one, I'll star it. Okay. Second is you would want the temperature to be controlled. Again, a little variation isn't going to make a big deal. All our data tables that we use in Chem 20 and 30 are pretty much all at SATP, standard ambient temperature and pressure. Okay? But we don't get hung up with a few degrees off. Okay? Last was that volume. Again, pH doesn't happen to be volume dependent, but most of our chemistry, if you put in more volume, you're going to put in more moles, and it's going to have a huge effect. Okay? So it's something you'd certainly want to control. So if you control those, you should be able to nicely tell a strong from a weak, and you should be able to order a whole bunch of acids. If you had 4 acids and you control all of their concentrations, the acid with the lowest pH would be most acidic, so it would be highest in the strength table. Second lowest pH, okay, would be your best weak, and you could order them all and build a table like this using their strengths. Okay? Or you could use indicators instead of a pH probe to build a table like this or to order things based on their strengths.